Brendan here. Welcome to Chapter 7. This is where we take the power of programming and turn it into our biggest safety net. We are not just writing code to make changes. We are writing code to stop bad changes. Archird is going to explain why a single digit can cost millions of dollars, and how we can use automated validation to make sure that never happens to you. Let us get into it.
Chapter 7. Using programming to catch mistakes before they ever happen. The best code you'll ever write is code that stops bad changes before they reach production. When automation runs without checking first. At 3:15 a.m. on a Saturday, a telecommunications company's automation system began deploying a routine network update across their infrastructure. The update had been tested in the laboratory. The deployment instructions were clear. Everything looked ready. Within 12 minutes, 420 network devices across Australia and New Zealand stopped working correctly. Internet service failed for approximately 380,000 customers. Mobile phone connectivity dropped for an additional 150,000 subscribers. The automated recovery systems couldn't function because they relied on the same broken network infrastructure. The problem wasn't a software bug or a hardware failure. The problem was a simple data entry error. Someone had typed 255.255.255.0 where they should have typed 255.255.254.0. A single digit wrong in a configuration file. The automation system never checked whether this number made sense. It simply applied the wrong setting everywhere, exactly as instructed. Recovery required 18 hours of emergency work by engineers manually visiting sites and correcting configurations device by device. Direct costs exceeded $5.5 million. Regulatory fines added another $2.4 million. The incident was entirely preventable with proper validation before deployment. This chapter explains how to use programming, specifically Python and structured data, to catch these mistakes before they ever reach your network equipment. The difference between doing and validating. Most beginners use programming to do things. Log in to the router, type this command, save the config. In a professional architecture, we use programming to validate things. Is this IP address valid? Does this change overlap with an existing service? Does the person requesting this have the authority to change this specific site? The 3 gates of validation. A safe system uses 3 different types of checks before it allows a single line of configuration to be sent to a router. Syntactic validation, the Typo Check. This is the simplest level. The code checks that the data is in the right format. Is an IP address actually 4 numbers? Is a VLAN ID between 1 and 4094? This catches the $7.9 million we discussed earlier. Semantic validation, the logic check. This is deeper. The code checks if the change makes sense in context. You might be trying to assign an IP address that is already in use elsewhere, or trying to delete a connection that a critical customer depends on. The code reads the whole network map and says, wait, if you do this, you'll break that. Policy validation, the permission check. This checks if the change follows the company rules. For example, no changes to the core network are allowed during business hours, or all firewall changes must be approved by the security manager. Why this makes you faster? It sounds like validation would slow you down. In reality, it makes you much faster. When you know the system will catch your mistakes, you can move with confidence. You stop spending hours triple-checking every line of code because you've built an automated assistant that does it for you, perfectly, every single time. Takeaway: don't just automate the work, automate the wisdom required to do the work safely. What you need to believe. If you implement one thing from this chapter, build validation that runs before deployment and rejects changes that don't meet requirements with clear, specific error messages. This single improvement prevents the majority of automation-caused incidents. Hard rules to take forward. Automation must be self-aware. It must understand the rules of the network it is changing. If a change violates a rule, the automation must refuse to execute and alert a human. Separation of data and logic. Store your network details, IPs, VLANs, site names, in a structured format like YAML or JSON, and keep your Python code separate. This makes it easier to audit and harder to break. Fail loudly and early. If validation fails, the system should stop immediately and provide a clear explanation of why. Never allow the system to guess or try to fix a mistake automatically. Validation is not optional. Every change, no matter how small, must pass through the same validation pipeline. Emergency changes are when mistakes are most likely to happen, so they need validation more than anything else. The effort invested in proper validation seems like overhead when building your first automation. The value becomes obvious the first time validation catches a problem that would have caused a production outage, or when auditors ask for compliance proof and you provide code and test results instead of policy documents. Building validation properly from the start is far cheaper than dealing with the incidents that improper validation allows through.
Validation is the secret weapon of the professional architect. It is what allows us to sleep at night, knowing that a simple typo cannot take down the entire company. If you have ever been saved by a validation check, or if you wish you had one, let me know in the comments. I would love to hear about it. In the next chapter, we are going to look at the execution engines, the muscle that actually makes the changes happen once they have passed all of our safety gates. I will see you there.